Markov and Chebyshev inequality. These are two inequalities that help us bound the probability of some unlikely events that we would like to not happen. Okay, so starting with Markov inequality, in this case we have a random variable x that can only take on positive values, and what I plot here is the density function that describes the distribution of x. You could use point mass distribution or other distributions. It's just easiest to draw when we're talking about the density. Okay, so that's the density, and the expected value of this distribution is, let's say, here at e of x. Okay. What we're interested to know is we want to upper bound the probability that x is very large. So clearly, if x is very large, it would make a big contribution to the expected value of x, and so that's how we get this relationship. Okay, so the way that we think about it is that we want to bound the probability of this region over here that I marked with green, and we are going to lower bound the expected value using this region and then using this region. Okay, so these two regions together make up the whole distribution. Okay, so the values of the distribution that are above A, we're going to map them all to A. We're going to move them, if you will, all to A. Okay, so we make them all smaller, and therefore reducing the expected value. And similarly, the values that are below A, we're going to move them to 0. And that will always decrease the expectation, because we don't have any values smaller than 0 that have non-zero probability. Okay, so that's the transformation, and this transformation, if you write it in symbols, it basically reads the following way. So so we can say that E oh, I didn't mean that. E of x is larger or equal to the part that is contributed by the green part, which is whose probability is x larger or equal to A times A, plus probability that x is smaller than A times 0, right? Because that's what we're going to do with that part. Multiplying by 0, then this part we can ignore. And now we can rearrange this bound to say probability that x is larger or equal to A is smaller or equal to the expected value of x divided by A. Okay, and that's the Markov bound. Okay, so now for the Chebyshev bound. Okay, so in this case we have a random variable that is not restricted to be just positive. It can be, here is 0, it can be negative or positive. And again, with the brown region, we represent the density distribution. And here we have the expected value that we now also denote by mu. And then we look at the regions that are away from we are interested in showing that the probability that the variable is far away from the mean is small. Okay, so we denote by sigma the standard deviation, and we say, okay, let's go up k times sigma, a distance of k times sigma, or down a distance of k times sigma. So in this case, the region that we want to bound its probability is actually has these two parts. Like this part is one, and this part is the other. These are the regions where the distance between the random variable x and the expected value mu is larger than k times sigma. Okay? So how do we do that? We basically are going to define a new random variable and then apply Markov inequality from the previous slide. Okay, so let's make some space here. Okay, and okay, so in this case, what we're going to do is we're going to just define a new random variable called y. I don't need that to be green. Y that is equal to x minus mu squared. Okay, so we just define it in that way. Now y clearly is a variable that is a random variable that is always positive, so we can use the Markov inequality for it. Okay, so we can just write probability that y is larger or equal to k squared sigma squared. Why I chose those I'll see in a minute. Is smaller or equal to e of y divided by k squared sigma squared. This is nothing but an application of Markov bound. Okay, so now let's see what do the two sides actually mean. If y is larger than k squared sigma squared, so basically if x minus mu squared is larger or equal to k squared sigma squared, then clearly what we have is that this is equivalent to x minus mu absolute value is larger or equal to k times sigma, right? Because if this condition holds, then x minus mu squared is larger or equal to k squared sigma squared, and if this holds, then this holds. So that's an equivalent event. Okay, and now what is EY? E of y is equal to E of x minus mu squared, which is exactly the definition of the variance of x. But that variance of x is also equal to sigma squared. So what we get here is that we have here at the this expression is sigma squared, and it divided by sigma squared, so we just left with 1 over k squared. So finally, combining all of these together, we get that the probability that x minus mu is larger or equal to k sigma is smaller or equal to 1 over k squared. Okay, so I hope this helps.